This video shows how the VART Eclipse plugin can be used to identify a regression fault not detected by the test suite of a software. We have an Eclipse workspace with two versions of a program that manages the stock of a store. If we compare the two versions, we notice that they differ for the implementation of function is available, that in version 2 returns -1 if an item is out of catalog. This function is invoked by function available products. Available products returns the total number of products available among the ones passed in a list. The diff of the two software versions also show that version 2 contains an additional test case, test 6, that tests the change by checking if function is available returns -1 when an item is out of catalog. We can check the correctness of the two software versions by running their test cases using the makefile. We can see that all the 5 test cases of version 1 pass. We then execute the test cases of version 2. We can see that all the test cases of version 2 pass as well. From this result, we may incorrectly assume that version 2 does not introduce any regression, but it is not the case. I am going now to show how VART can be used to spot the presence of a regression. We use an empty project to store VART analysis data. First, we create a VART configuration using a wizard. We give the configuration a name, store. We then provide the location of the source folder for version 1 and then indicate the executable of our program. We do the same for version 2. VART relies upon dynamic program analysis and model checking to identify regressions. In the next window, we can indicate the model checker to be used, CVNC in this case, and its options. When we press Finish, VART automatically detects the modified functions and creates configuration scripts that will be used for monitoring. If we right-click on the generated configuration file, we can identify regressions by pressing on Verify Upgrade in the VART contextual menu. During its analysis, VART automatically monitors test cases execution. The analysis runs in the background. We can see that VART creates temporary folders which are used to store runtime data collected during monitoring, derive properties, and copy the software versions used to run model checkers. Once the analysis finishes, VART results are reported to the end users. In particular, regressions are reported in the problems view, in the form of violations of program properties expressed as assertions. The Eclipse editor is annotated by VART with information about the program properties violated at each line. This annotation, for example, shows that function available products violates two properties: return greater than 0 and total greater than 0. This indicates that the upgraded software violates properties of the base software that should hold for the upgraded software as well. We are in the presence of a regression. Recall that function available products is one of the callers of function is available, the function modified by the upgrade. Please note that the two properties have been automatically identified by VART by analyzing the data collected during the execution of the test cases for the base version. A list with all the regressions found by VART is also shown in the regressions view. The view VART debugging instead shows also the updated properties and the properties that are valid for both the two versions. Outdated properties are properties intentionally changed by developers according to VART. The annotations in the text editor are automatically updated to include all the properties reported in this view. A warning on the last instruction of function is available indicates the presence of an outdated property. This outdated property indicates that the return value of function is available is no longer equal to just 0 or 1. This information helps identifying the change that caused the regression. To further speed up debugging, engineers can select an invalid assertion and generate a counterexample trace that shows how a concrete input may lead to the property violation. In this case, we select the assertion indicating that the return is positive. Counterexample trace is generated without executing the software. We inspect the trace backward from the bottom, that is, from the property violation. We observe in the right panel the variables that are updated by the instructions selected in the trace. Line 28, for example, assigns value -2 to variable total. It is clear that this assignment causes the regression. We go back one step further and we observe that this is the consequence of adding -1 to the current value. -1 is the value returned by function is available. After inspecting the trace, it is clear that we can fix the regression by handling the case in which -1 is returned by function is available. If we re-execute VART, we can see that we fixed the regression. No violated properties are reported and all the non-regression properties are valid also for the upgraded version.